We're going to look at finding the outcomes of compound events. So the essential question is, how can all of the possible outcomes or the sample space of a compound event be represented? So if we look at this on page IN7, Cameron packed 2 pairs of shorts and 3 t-shirts for a weekend trip. What are some combinations of shirts and shorts that Cameron can wear while on his trip? How many days will he have a different outfit to wear? So we can look at this. One way of doing this, we could maybe draw lines between the different options. Might get a little crazy with all those lines. We could make a table or tree diagrams we've talked about before. For example, yellow shirt could go to green shorts, or what are those, navy? Blue, we'll call them if you want. The white shirt could go to green shorts or blue shorts, and the red shirt could go to green or blue. So you could look at all the different routes you've got, or you could just, if you wanted to, instead of that, you could write them kind of as ordered pairs, kind of like when we graph things. Yellow, green, yellow, blue, and so on. Okay, so how many different options does that give us then? 6 options. Okay, if I had a lot more of these, say we had 7 shirts and 10 pairs of shorts, would you want to do that with all these? Not really. Okay, so we will get into later, we talked about it before, I think, a quicker way of doing this. Actually, we're going to be able to look at how many shirts we have and how many shorts we have, and we will make quick work of a problem like this. So how many shirts we got here? 3. How many shorts? If you actually just multiply those together, that will tell you how many options you have. So 3 times 2 is 6. We have 6 different options of outfits to wear. Example 1, Haley has 2 sisters and no brothers. Josh has 2 brothers and no sisters. They wonder what the chances are in a family with 3 children that the children will be all boys or all girls. How can they determine all possible combinations of boys and girls in a family with 3 children? So this is a compound event. The book talks about it here. A compound event just means we have 2 or more events. So if there's at least 2 things happening, it's a compound event. So in this case, like the book says, we have 3 events for this particular problem. As long as there's at least 2, though, it's a compound event. So what they did here, they listed out some options. So the first child could be a boy or girl, second one could be boy or girl, third one could be boy or girl. And then they made a tree diagram here, looking at the different routes that we could take. So we could start out with the boy, and then we could work down this way. We could have another boy, or we could have a boy and then a boy and then a girl, or a boy and then a girl and a boy, and so on. We follow all the different routes that we could take, and you can kind of see as you look through that, underneath these last ones, they put kind of a final detail of what's happening. All 3 boys, boy, boy, girl, boy, girl, boy, boy, girl, girl, and so on. And you can see there's actually 8 different options. If you look at this to see the options for having 3 boys, the book doesn't really give a final answer for this. 3 boys, how many routes had 3 boys? 1 out of how many total? 8. So there's a 1/8 chance, if there were 3 children, that they would all be boys. Right?
I have 3 other brothers, so they're all boys.
Okay, so yours is a 1 out of 16 chance there we can talk about. 3 girls, what's the chances? Is also 1/8. Okay? And then we could go on from there. We've got, another possibility would be 2 boys and 1 girl. So 2 boys and 1 girl. There's one, there's one, there's one. So that's a 3 out of 8. And then we could have 2 girls and 1 boy. 2 girls and 1 boy. 1, 2, 3. So that also would be 3/8. Okay? Those are actually our 4 possibilities here. So those, when you add those probabilities together, those add up to 8/8, which is the same as 1. Okay? And that means like 100%. So that's what should happen if we have all of our different choices. A different way we could talk about, rather than drawing this out, another option you guys have, if you're wanting to find, we'll get into this more later, but if we were wanting to find the chances of getting all 3 boys, for example, okay, what this means, the P stands for probability. This is saying probability of boy, boy, boy. And basically we just think about what's the chances of it being a boy, first of all. Would be 1/2. Then the next one, what's the chances of it being a boy? 1/2. Next one, what's the chance of it being a boy? 1/2. And actually, if you just multiply those probabilities together, that will give you that probability of all 3 boys. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. And we got the same answer we did with doing that tree diagram. So again, just kind of a preview there of what we'll be talking about. One of the things later we'll be learning more about. On the try it, Jorge will flip 2 quarters at the same time, complete the tree diagram, and then list the sample space for this compound event. Use H for heads and T for tails. Okay, so one of the things is they talked about doing a sample space, and we haven't really talked about that yet. So let's get a definition here for sample space. Sample space is a list of possible outcomes. So it's kind of like, what could happen. So like, for example, if we are rolling a die, singular of dice is die, we're rolling a die, our sample space, our possible options would be 1, 2, 3, 4, 5, 6. Assuming that it's a normal die. There are other ones we could talk about that might have more than 6 sides, or they might have some weird stuff like having a 6-sided die that has a 0 on it, or it might have addition, subtraction, multiplication, division symbols on it or something. But normally 1, 2, 3, 4, 5, 6. When we list a sample space, you'll notice on the sample space I put these braces here. Not like the braces on your teeth, but these braces, that's just how they write sample spaces with those around it. Kind of like we put ordered pairs with parentheses around it. Alright, so on this problem, we're talking about flipping 2 quarters. So if we want to look at our tree diagram first of all, the first quarter we might have got heads, and then off of that the second quarter could have been heads or tails. Okay. Another possibility, our first quarter could have been tails, and then off of that we could have had, besides tails, we could have had heads. Okay, so we can see the different routes here. If we look at this, we got 1, 2, 3, 4 different routes. Means on my sample space, I should have 4 different things. So the sample space is just looking at the different routes here. So our sample space, we'd have one option would be heads, 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 tails. What else? Tails, heads, and tails, tails. Good. And however, whatever order you want to put those in, as long as they're all 4 there. Example 2, a game is played by spinning the 2 spinners shown. Players match the results of the spinners to combinations on their game cards, kind of like bingo. How many different combinations are possible? So what they did here, they made a table, and they're actually using their table to represent their sample space. So rather than listing all these out in one big line, this would take quite a bit of room. They're actually using a table here, and that's okay too. So options A1, A2, A3, A4, A5, A6, B1, B2, B3, B4, B5, B6, and so on. Okay, you can see here we've got basically a rectangle or a square here. If you look at this, there's 6 options this way. There's 6 options this way. So 6 times 6, there are 36 different possibilities. And a way of getting that, besides just listing them all out, if they just said how many different possible outcomes are there, we could use what's called the multiplication counting principle. This we talked about earlier in the lesson. Multiplication counting principle. If there are m outcomes for one event and n outcomes for another, their combined outcomes can be found by multiplying m times n. So in other words, this problem we had 6 letters, we had 6 numbers, so we could just multiply 6 times 6 to get 36. Tells us how many possibilities there are. Okay, another name you might see for this, rather than the multiplication counting principle, sometimes it's called the fundamental counting principle. Example 3, Stan will roll a number cube labeled 1 to 6 and flip a coin. How many outcomes are there? What are all the possible outcomes? So if the question just was how many outcomes are there, we could just use that fundamental counting principle or multiplication counting principle. We could say for the number cube we've got 6 options. For the coin we've got 2 options. So to find how many outcomes we could do what? Multiply. So that's what they did here. 6 times 2, there's 12 possible outcomes. Even though it asked me to list them all, it's still not a bad idea to do that, just to remind ourselves how many options we should have when we list them out, to make sure we wrote them all out. Okay, so once they did after that, then they listed out their possible outcomes over here. So possible outcomes, we've got 1 in heads, 1 in tails, 2 in heads, 2 in tails, and so on. And again, double check yourself that you got 12 different options listed there. So if we look at the try it, a bag contains tiles labeled with the letters A, B, and C. A box contains tiles with the numbers 1, 2, and 3. June draws 1 letter tile and 1 number tile. Use the multiplication counting principle to find the number of possible outcomes, and then represent the sample space using either a table or an organized list. Alright, so if we think about this, we're going to do 2 things here. We're going to get a letter, we're going to get a number. So with the letters, how many letters do we have? 3, okay. And the numbers. Okay, so 3 letters, 3 numbers. So to find how many different options we have, what will we do with those? Multiply. So we multiply these, so we do 3 times 3 would be 9. So there's 9 possible outcomes. And then we can list out our possible outcomes. So possible outcomes, we could have A1, A2, whoops, A2, A3. What else? B1, B2, B3. Good. C1, C2, C3. PO. Oh. Okay, so we can see then there are our 9 possible outcomes. We know we've written them all there. So key concept, we talk about compound events. Again, is if we have at least 2 events happening, that's called a compound event. We can use an organized list, a table, or a tree diagram to represent the sample space. Again, the sample space is just a list of all the possibilities. So you can see how they've done that with heads and tails, flipping 2 coins there. And then the multiplication counting principle or fundamental counting principle can be used to find the total number of possible outcomes. So in this case, we have a coin. We flip a coin. We flip a coin. 2 options, 2 options. We multiply, we get 4. When you guys do these problems, if you do a multiplication counting principle or fundamental counting principle, I would recommend that you put a little blank or a little line for each thing that's happening. Each time something happens, you need another number that you're going to multiply together. We'll talk about that more in a minute. So if we look at the do you know how number 4, both spinner A and spinner B have equal size sections as shown at the right. Use the multiplication counting principle to find the total number of possible outcomes when both spinners are spun. So you can see we have 2 spinners being spun. We have spinner A and a spinner B. So I'm going to draw 2 blanks here. For spinner A, how many options do we have? For spinner B, how many options? So if we multiply 3 times 3, would be 9 possible outcomes. Good. Okay. Part B says make a table to represent the sample space when both spinners are spun. So making a table, we can kind of look and put on the outside the different parts here or different options. So maybe on the sides here, if we put our numbers, let's say we got 1, 2, and 3, and then we've got red, blue, and green, huh? Somewhere on our table we should actually spell out the words red, blue, and green so that if somebody's just looking at this they can tell exactly what's happening. Once we've done that, now we can abbreviate since it's on our table. So we just look, this is kind of like what you guys have done before. You've seen multiplication tables and things. That's kind of the same idea. So this top corner here starting out, we'd have 1R, 1B, 1G. Again, we can abbreviate because the colors have different letters they start with, and we've already mentioned them on our table. Okay, second row we would have 2R, 2B, 2G, good, and the last row 3R, 3B, and 3G, good. And if we look at this, we do have 9 possibilities there, which matches up with our answer for part A, so that should be good. Okay, we look at number 5. Tiles labeled with the letters X, Y, and Z are in a bag. Tiles labeled with the numbers 1, 2, and 3 are in a box. Make a tree diagram to represent the sample space of the compound event of selecting one tile from each container. So if we start out, let's say we start with X, branching off from X, that's how they get this tree diagram because it's got branches. So off from the X we could have what? 1 or 2, is that it? Okay, we could have Y branching off 1 and 2. We could have Z branching off 1 and 2. Okay, and a way of checking that, we have 6 different options or routes here. If we look at this, letters, we have how many letters? 3. How many numbers? 2. 3 times 2 is 6. We had 6 routes, so we should be in good shape there. So on page IN11, let's do numbers 6 through 8 and 10 through 15.